Hello and welcome everyone. This is an introductory demo video showcasing the programming framework components of the Smart Collectives Toolkit developed within the Work Package 7 of the EU's FP7 Smart Society project. So the purpose of the goals of our work package were to develop the virtualization and communication functionality as well as a programming framework that would allow end users to exploit the functionality of other Smart Collectives Toolkit components through a simplified and familiar interface. In lines with the stated goals, the outcomes of our work package were a virtualization and communication middleware called SMARTCOM, a set of programming libraries and associated programming API, as well as a number of subcomponents and APIs that allow integration with other Smart Collectives components. And all these are actually described on these two websites. The first one providing more technical level and theoretical background in forms of deliverables and technical reports. The latter one providing a more high level and user-friendly description of the results of these theoretical findings in terms of implemented components. So to give you a better idea of the relationship of the WP7 components and the remaining Smart Collectives components, we show here the envisioned architecture with all the principal components connected together, where our components from WP7 are more enhanced. And we refer to this figure as a Smart Society platform because it is, but in reality is a one possible configuration of different Smart Collectives components, allowing a full end-to-end implementation of a hybrid diversity-aware collective adaptive system. It is of course possible to have also less advanced, not fully fledged configurations with less integration, which might be appropriate for different or simpler or more scenario-specific uses that leverage different Smart Collectives components. However, for showcasing the intended usage of our component, we make use of this particular architecture, which we will describe shortly now. So basically, as you can see here, we have the three types of entities that the platform interacts with: the users, the developers, and human or machine peers. So the users are the actual end users that send requests through their devices or websites to our platform, which receives them through a unified API, and then depending on which application they belong to, dispatches them to this particular Smart Society application. An application runs in a container, which is in order to basically be able to initialize specific components such as Java Virtual Machine, our communication middleware, and also if needed specific Smart Collectives components that are not offered as services but need to be started as a standalone component. And of course, the actual application is, it is an arbitrary code that needs to be provided by someone, and this code is provided by the developers, and it is of course can be scenario specific and offer any additional or specific functionalities required to process the user or the user's request. But then when the developer's code needs to or wants to make use of the advanced functionalities offers of our platform, he invokes from his code through our programming API the different programming model constructs, programming framework constructs through which we expose the remainder of the platform's functionality to the developer. So these functionalities are advanced communication, which we'll be talking about a little bit later, advanced negotiation, composition and orchestration, monitoring, algorithms, and then as well really a privacy preserving and privacy respectful way of handling the private data and managing profiles of the participants, and also a way to incentivize the human participants of these tasks. So these all taken together allow very powerful functionality that is then exposed, as I said, to the developer, and then thus ultimately also to the user who submits the request. But they are under the control, under the control of the programming framework, ultimately. And just to briefly explain that the peers need not necessarily be humans. They can be also machines. And when I say machines, I mean either web services, but also possibly sensors that are represented through their gateways, or actuators that might also be performing some activities in the real world. And the web services can be there either to actually perform some computational functionality, or as a support functionality, such as collaborative or communication environment, or for the human peers that are in the collective. But the whole point is that all these peers, as we call them, are uniformly treated by the platform, and this complexity in this communication and management. Now on to the first major contribution of the WP7, the SMARTCOM Middleware. Here we show you the actual basically operational context of SMARTCOM and describe its virtualizing role. So as you can see here, and as we mentioned, we have the ability of engaging through our platform different types of entities, human entities, web services, or even controllers, if we develop such kind of interfacing code. So basically controllers which can, or gateways which control sensors or actuators. So in order to allow a uniform handling and communication with all these diverse entities within collectives, which can be composed of these diverse participants, which we refer to as hybrid collectives, we need a way to virtualize the communication, in this case with these peers. So each peer's participation is described by a specific context, for example, execution context, different incentives in case of human peers that can be applied, quality of service provided. But middleware, the SMARTCOM middleware is primarily concerned with the communication, and based on the described communication context, it is able to translate the communication towards a specific peers into an acceptable format and transform back the responses. It knows how to and when to accept specific requests, whether to retry delivering them, and so on and so on. On the other hand, for the developer, the interface for the communication is really simple. The developers only see collectives, not individual peers, and they just say, I want to deliver this message or communicate with the collective, and then all the rest is handled by the SMARTCOM component. So this is basically a simplified internal architecture of SMARTCOM. I will not go into details about specific subcomponents of it. I just want to kind of showcase that basically what we have are these specific adapters, and these adapters can be used to communicate with specific peers using some familiar communication channels such as emails or Google Android notification that are actively pushed to the devices. There we have Twitter adapters that allow basically to mention specific users in tweets and collect their responses from their tweets with specific hashtags. We also then have, let's say, non-direct communication channels supported, for example, Dropbox, where you can communicate with someone indirectly by basically uploading something to a given and dynamically created Dropbox repository for you, or uploading a file, or sending an email, not directly to another peer because you don't know him perhaps, but to a specific email address, and then the SMARTCOM takes care of the rest. It also takes care of specific delivery policies, group delivery policies. How do you interpret when you message a whole group? What is a successful message delivery? Is it to the whole group, to a majority, to specific people? Do they need to acknowledge that they have received the message? Is it the best effort attempt? So basically it handles all these and supports all these use cases, and these are actually don't need to be always specified by the developer, but actually they can be decided also by the system itself or the collective itself based on their privacy and delivery policies. So what SMARTCOM tries to do is really shield the developer as much as possible from all the intricacies of group-based communication via different communication channels. In addition, handling the privacy of the human peers, and this is really an important aspect of it, because it allows that peers individually, human peers in this case, specify exactly when they want to be contacted. If they can also specify if there is someone who shouldn't be contacting them at specific times or at all, and they can also specify at which times they want to be contacted through which channels. So these things are all possible to set up, and basically the developer then just needs to say, I need to deliver this kind of message to the collective, and all the remaining checking of these policies and actually performing of the communications handled by SMARTCOM. So the figure shows the envisioned usage of the programming framework. Developer is using our programming API to integrate the capability of the Smart Society platform at arbitrary places and times in his code. And he does that whenever he wants to solve a task collectively. When we say collectively, this means that different peers can be made part of a collective, and basically either they will on their own decide how to solve it, or basically a set of activities that they would need to solve will be composed for them by the platform itself. In order to concretely for different scenarios, of course, different approaches can be used, and this is ultimately what the platform is there for. But in any case, some specific execution will be always composed of different phases, which will differ per scenario. In this case, we have here the basic phases of provisioning, composition, negotiation, and execution. And at each of those phases, different peers might be taking part, and after each of these phases, different collectives might be formed. So while these specific phases are not under direct control of the developer, he can check at which stage a task is, and he can also access different collectives that get formed throughout the execution, so that he could perhaps communicate with them, reward them, monitor them, develop a, let's say, more long-lasting relationship of confidence between two of them. Although this is what exactly he can see of a collective and what he can access is pretty strictly regulated, as we will show a little bit later on. But the whole idea is that the developer is able to work with two principal components: collective-based tasks and associated collectives. Now the collectives is one of the theoretical novelties that we are introducing. The point is that we have really put the collective to be the first-class citizen of our programming model. So it is the collective is actually the atomic construct and not the peer. I mean, at least this is how it is exposed to the developer. So instead of working with individuals, the developer needs to think in terms of problems and collectives that solve them. So, okay, I mean, in the actual prototype implementation that we will be showcasing in our remaining videos, and here it is possible to get to the individual members through reflection, but this wasn't the goal of the basically proof of the concept implementation, but it was rather to motivate the developers not to think in terms of individuals, but rather in terms of collectives. So if this philosophy is going to be respected, then the developer will be able to use our functionality in the intended way. So let's talk a little bit about the collectives. A collective can be many things. It can be a large group of people that identify themselves as a long-lasting group, for example, Manchester United fans. It can be also a group determined through categorization over specific attributes, such as citizens of Vienna, for example. And in both of these cases, we talk about a resident collective. As you can see in this case, it's not really that the members themselves decide, I'm now part of this member ad hoc, but they can be also passively categorized as such. And it also, in this case, the collective itself is not defined by its members, but by some more long-lasting characteristics, and the actual membership can vary throughout time. On the other hand, we can also have different type of collectives, which we call application-specific collectives, but in reality the key point is that they are more ad hoc. They are created for a specific purpose. They are a team of people or other devices and software, so team of peers, and assembled for a specific purpose with possibly predefined roles and activities to be performed. And anyway, once formed, this collective, of course, can become a longer lasting one, but the point is that it was formed with such purpose, and at the moment of creation its members were precisely defined, and from that point on it is not possible to kind of say that the membership is now different. So this is the main difference. So the resident collectives are defined by their properties. They're usually long lasting, but their membership can vary, and we can actually also see exactly who those members are because we queried for them. The application-based collectives are shorter lived usually. They can be persisted as longer one, but they have been usually assembled by the platform, which means that they are an atomic element for the developer, so it shouldn't at least be able to see the members of it, but really treat them as the principal entities that work on specific tasks. This is actually the reason why we decided to do this is that we can in this way we can really shield the developer from deciding the composition of this collective. We can transparently to him change if we want as the programming model the composition. We can enforce the privacy and fairness policies, which was actually the guiding idea behind this. And as also mentioned, we really are trying to impose the strategy of thinking in terms of collectives and not specific individuals on the developers themselves. The collectives here are handled in a very privacy respectful way, and this is achieved by integrating our programming model with the peer manager component, which was developed by our project partner, the University of Trento. You can find more details about the peer manager in the materials provided by them on the website, but we really rely on them to as the provider of what is shown here in the figure as the peer store. This peer manager is one possible peer store, and it is really important for us because this means that we are able to delegate all the sensitive privacy handling, privacy management to the peer manager, because it allows us as the programming framework to work with the minimal necessary amount of personal data that was personally authorized by the peers themselves or by the policies in place at the peer manager. In addition, the programming framework does not need to store any private data locally, which significantly lowers the risk related with working with human personal or private data. On the other hand, for such applications where privacy is not an issue, for example, when we work primarily with anyway anonymous people or software peers, and also when we, for demonstrative and testing purposes, the programming framework does also implement a local MongoDB storage implementing the same interface as the peer manager. but without any advanced privacy handling functionalities. The second principal member or element of the programming model is the collective-based task. The collective-based task is basically the task that the developer initializes when he wants a request being processed by our Smart Society or Smart Collectives platform components. The collective-based task is in reality a wrapper around an arbitrary task model adopted for the specific application that the developer is writing, allowing it to be executed on our platform. In this respect, we say that our programming framework is task agnostic. In reality, collective-based task is a set of predefined phases and transitions between them in form of a state machine, allowing the execution of specific phases in different orders. For each phase, we assign a different handler that actually contains the business logic for the execution. In many cases, the business logic can be standardized and provided by the programming framework library, thus taking off the burden of the developer and making our programming framework more general and versatile. For example, we can offer multiple algorithms for provisioning and assembling collectives. We can expose the functionality of the remaining Smart Collectives components through the library handlers in a very fast way for the developer, like, for example, the complex orchestration and the negotiation algorithms that were used for agreeing on rights in the ride-sharing scenarios that were developed by our colleagues and project partners from the University of Edinburgh. The execution handler shown here at the bottom is the only handler that is usually not library provided, but rather encapsulates, it is automatically generated from the business logic provided by the developer, although in theory it can be also library provided, but it usually isn't, because the developer usually is the one who knows how to handle application-specific task requests at the lowest level. For example, what kind of task description should be sent out to peers, what kind of results are expected, how the results can be interpreted in terms of quality of result, what are the timing requirements, for example, maximal duration of the task or a cutoff deadline. Also, what is the condition for considering an execution successful or not. So if we offer most of these handlers as library components, this really allows the developer to develop, to initialize and to put to use these collective-based tasks quite fast, which means that he only has to parameterize the handlers, and he's basically able to let them do the work. And not only that, but even though many of the handlers could have been developed initially for the specific application, they can also be used generally in similar applications. For example, our ride-sharing application can be generalized to sharing applications where multiple people need to agree on how to share a joint resource and to agree on joint time and conditions of this usage. So it doesn't necessarily have to be a car. So in this respect, we believe that really the generalization potential is quite high, and the good thing is that you can still use exactly the same programming model and these collective-based tasks to execute different specialization of these algorithms, and this is why we were able to say that we are as the programming model task agnostic. So we will be showing an additional demonstration videos which will be showcasing a code walk through some concrete examples in our repository. But just to give you a brief idea of how one can use the CBTs and collectives from in this case only CBTs from the program. General, this is basically how it looks like. This is some pseudo code shortened one, and so as you can see here in the top, you initialize some existing handlers, in this case those that are coming from our one of our previous demo applications as Smart Society. Parameters are provided, the handlers are there. These handlers are then used here in line 11 to initialize what we call a task flow definition. This is an intermediary structure to initialize our collective-based task. Optionally, one can also specify which collective can be used as the initial input collective. Otherwise, a predefined default one will be used. In this case, we use nearby peers, which is simply peers that have applied for participating in this application, that are currently marked as available and that fulfill specific distance metric criteria. So once this task flow definition is specified with the initial collective-based task can be simply built, and it can be passed a task request to solve, and then simply started. So we will see now in the next slide how the actual runtime can be monitored and controlled. But basically, after the CBT has been started, a new thread is started, and the developer can keep on doing what he wants and then just come back to check for the result. So basically, this example now shows you how the developer can control the CBT lifecycle. This is a contrived example where we want to locate a number of Java developers, then have them agree on who of them will be participating in the task. And then, of course, they have to fulfill specific quality criteria that we specify. But after they negotiate and agrees of them, they agree, they can start working together on the programming task, whereas the remaining Java developers that that couldn't make it into the initial team are then leveraged as a test team. So of course this is not realistic, but it's just meant for the demonstration purposes. So let's go briefly to what we do here. So first we parameterize the handler for negotiation. So in this case, we just say that any collective in which everyone agrees with the membership of at least half of the other members is acceptable. So in this case, we can form a number of acceptable teams, and then these acceptable teams have to be actually definitely agreed upon by all the members that will participate, and the first one that gets to agree it then becomes the executing collective. So we specify basically this thing so passively, so it is and then the actual negotiation takes place only after the programming task, as we call it in this case, has been started. So as said, it's in parallel in this other thread the negotiation takes part, and we are only interested here in checking when the negotiation will be successfully finished. So we know that since the pattern we used to control the negotiation, that at some point there will be a team that will be be mutually in agreement and will have accepted to work on the task. Of course, in this case, we do not consider the case when they couldn't have agreed, but we didn't go through these things. But we also have these different strategies that are there exactly to handle such cases. So how do you restart or fail graciously the CBT in these cases? In this case, we just accept that they have successfully negotiated and there is now a collective that has accepted to work on the task. And then in this main thread here on line 19, we check that this agreement has been reached, and then form another collective by complementing. So it's just taking those that were selected to be initially considered, but haven't really in the end ended up in the agreed collective. So the one that was the first to agree together to work on the task. So out of these people, which we also consider obviously worthy of doing this, we offer them to work on testing the artifact that the initial collective will perform. So as I said, once again, not a realistic thing that much, but just there to showcase how things can be used. And then, of course, we can wait until the full execution is done, so of the programming task. So when the software artifact is only done, and only then engage the new test collective to work on the output of the first task as their input task, and also to control in the end the quality of result. So what is the quality of result, how many tests have passed. So this thing also doesn't need to be necessarily done manually by the developer. It was just also shown here to show that we also offer these kind of things directly to the developer, but basically deciding on the quality of result and whether an outcome can be accepted or not can also be encapsulated and hidden from the developer, so that he really doesn't need to worry of knowing exactly the metrics that are used and the threshold with which they need to be compared. So basically that was it for this brief introduction. As I mentioned before, we will be providing additional videos with code walks and concrete examples, and showing you how to use them, how to run them, and explaining concretely these concepts that were just briefly introduced here. For additional information, the three important websites for you to check out are the website of the project itself, which contains links to the various deliverables and technical reports that describe the technical background of the components and some concrete APIs in more depth. Then the Smart Collective's website, which offers now the implemented technical concepts in the form of a set or a software toolkit of mutually interoperable or compatible components, which need not necessarily be used all at the same time or all together, but present a coherent view on the concepts that were introduced in the various deliverable. And regarding the programming framework, this is the Git repository that we use, that is open source, and you can go there and check out the code and the examples. Let me also just briefly use the opportunity to thank the European Union and the Smart Society project for supporting our research and financing it, and also my colleagues at my own research group, the Distributed Systems group at the TU Vienna, as well as all our partners on the work package itself, the University of Edinburgh and U Hopper from Trento, Italy, as well as all other colleagues and researchers from the project itself, and our partners, which are also listed here, as well as the FOCUS initiative of the EU, which was also highly supportive in connecting the various interrelated projects that deal with collective adaptive systems. Thank you and have a nice day.